The first thing we're going to talk about today is how we can develop these identities for cosine, sine, and tangent double angle. In class, we talked about how we can start by expressing cosine 2a as a plus a. And once we have it written as a plus a, we can use our cosine double or our cosine sum formula to get this top line here. And after condensing, we get that cosine 2a equals cosine squared a minus sine squared a. And this is our first of three formulas for the double angle for cosine. Now we talked about how it's not always practical to have a formula that only has, or that has two different functions in it. It would be more practical if we could have one formula that only used cosine or only used sine. And so in order to make that happen, we utilize the Pythagorean identities. And we rearrange the Pythagorean identity for both cosine squared and sine squared. So in this second formula, you'll see that we replaced the cosine squared a with 1 minus 2 sine squared a and then simplified, giving us equation 2. And then in our third formula, we replaced the sine squared a with 1 minus cosine squared a, giving us our third formula down below. A couple of the observations we made are that in general, the cosine squared function is the positive one. That's why it is the first function or the positive function. And the sine squared function is the negative one, which is why it is the second function or the one that is being subtracted. Those are just a couple observations that we made in class. After that, we went ahead and looked at the double angle identities for sine and tangent. And we saw that the way that we went ahead and found our cosine formulas also worked for sine formulas. We could express it as a plus a and then do our sum formula. For sine and tangent, there are not alternate forms of the equation. What you see is what you get. And so in this lesson, we have a total of 5 formulas that we want to make sure we're keeping track of. Alright, from there we went ahead and did some examples to apply this information. And one of the big things that I talked about is that now that we're talking about theta and 2 theta, it's important that we realize that these are actually different angles. And just like how we made a double XYR chart before with angles A and B, we can do the same thing with angles theta and 2 theta. And at this point, we just want to fill in what we know. We know that cosine of regular theta is equal to negative 12/13. So that gives me my x is going to be negative 12, my r is 13, and we know based on triples that my y is going to be 5. We are also told that sine of theta is positive, so we know it's going to be positive 5. Now that we know our x, y, r values for theta, we can go ahead and solve for all of the following: cosine 2 theta, sine 2 theta, and tan 2 theta. So if we use our first, our formula for cosine 2 theta, here I would recommend using the formula of 2 cosine squared theta minus 1, simply because cosine theta is what was given to us. So when we go ahead and work this through, this is just going to become a lot of algebra, which again we will not have a calculator for. And so we end up doing 288 over 169 minus 169 over 169, which gives us 119 over 169. Now this solution that we have right here, not only does this tell me the cosine of 2 theta, this also tells me the x and the r for angle 2 theta. So I can plug in 119 over here for x and 169 for r. Now in this problem, it's not practical to do x, y, r to solve for y because I don't have a calculator. However, once I find either the sine or the tangent, I will know the y value, and then I can use x, y, r to finish the problem. Alright, now when we try to determine which one we want to do, the formula for sine is way easier to work with than the formula for tangent. So I'm going to go ahead and do my sine formula. And for the sake of room, I'm just going to write it down here. So sine of 2 theta equals 2 sine theta cosine theta, one of the formulas we just learned today, which will give me 2 times 5/13 times negative 12/13. And then when we multiply this across, 2 times 5 is 10 times negative 12 gives me negative 120 over 169. Because this is a sine, that's going to tell me my y over r for angle 2 theta. All right, so the r value matches, which is a good thing. That's what we expect. We now know that the y value is negative 120. And now that we know the xyr for angle 2 theta, when we want to go ahead and find part C, and in part C we're trying to do tangent of 2 theta, I can simply do y over x for angle 2 theta, which will give me negative 120 over 119. Now, if we would have worked through the algebra and actually solved it all, we would have gotten the same answer. So we can do that, absolutely. However, we've got to be careful because if we do a lot of unnecessary algebra, that's where we run out of time on a test or a quiz. All right, in example 2, we're going to utilize that same idea of doing a double XYR chart, this time again using theta and 2 theta. So we will have XYR, theta, 2 theta, and we'll fill in what we know and what we find as we find it. All right, so we know that for angle 2 theta, cosine is 4/5, which means I have 4 for x and 5 for r. We also know that for regular theta, sine is positive, so I can put a plus sign right here. All right, now we're going to go ahead and solve for what we don't know. Since I know cosine 2 theta and I'm trying to find cosine, the formula that I'm going to use is cosine 2 theta equals 2 cosine squared theta minus 1. Again, we have 3 choices to work with. Since we're trying to solve for cosine, that's the formula that we're going to use. All right, so we're going to plug in the 4/5 that we know. And then at this point, this now comes down to doing a lot of algebra. So first I want to add 1 to both sides. And when I add 1, since I'm going to be adding it to the fraction 4/5, I'm going to think about it as adding 5/5. So that way it makes my fraction work easier. So now I have 9/5 equals 2 cosine squared theta. And I want to get rid of this 2. So I'm going to think of it as timesing by 1/2 because that'll make my fraction work easier on the left, giving me 9/10 equals cosine squared theta. And then from here I want to square root both sides. Now when I square root both sides, I'm going to end up getting 3 over square root 10 equals cosine theta. Now we know that we don't want to leave our answer like this and we want to rationalize it. However, for the purposes of our XYR chart, I would recommend using the unrationalized values in your XYR chart. And the reason why I suggest that is because these values are much simpler to work with. They'll be easier for Pythagorean Theorem. So we know we're going to have a 3 for x, we're going to have a root 10 for y. So now when we do our Pythagorean Theorem, 3 squared is 9 plus y squared equals root 10 squared, or just 10. Well, then that tells us that y is going to equal 1. And now that we know x, y, and r, well, now the rest of our work is simple. When we're coming up with our cosine, sine, and tangent, we can simply use x, y, r values and rationalize our answers. So my final answer for cosine theta is going to be 3 root 10 over 10. My answer for sine theta will simply be 1 over root 10, which is root 10 over 10. And then my answer for tangent theta will be 1/3. We could obviously have done all of the formulas, we could totally have worked through them, but XYR is a way simpler way to do the problem and definitely saves a lot of time. Alright, with this last topic, here we are going to be manipulating our equations. We're going to be looking at these expressions and trying to figure out which kind of formula does it most closely match and how can we manipulate it to simplify without a calculator. So there's going to be 3 steps I'm going to suggest you do. The first step I'm going to suggest you do is identify which formula it resembles. So for example, when I look at problem A and I see cosine squared 75 minus sine squared 75, I want to be able to look at those formulas that we wrote down and figure out which one does it look the most similar to. So which one does it resemble? It may not be an exact match, but which one is it closest to? Then, once I've identified that formula, I'm going to write the base formula the way that it should look. So what would I expect it to look like if I was copying it off my formula sheet? And then, lastly, I'm going to modify both sides of the equation to match the given problem. Okay? After I have modified to match the given problem, then I can simplify the other side to solve. Okay, let's go ahead and see how this works out for the 3 examples on this slide. To make it easy for discussion, I labeled the equations with numbers 1 through 4 off to the side. So if we look at problem A most similarly looks like equation 1. So I'm just going to label that with a 1 right now. Equation B, that one most closely resembles equation 4. And C most closely resembles equation 2. Okay? So now that we've identified the equation, what we're going to do is we're going to write the formula the way that it should look. Now, something I want you to understand is that whatever angle we see as angle A, when we write it as a double angle, we are actually going to double that angle. So for example, if I see that I have cosine squared 75 minus sine squared 75, I can say that that is equal to cosine of 2 times 75. Okay? Now when I look at this right-hand side, this is a match to my given problem. The way that the formula is, without any modifications, is a direct match. So what does that mean? Well, that means that this expression is equal to cosine of 150. And I know what cosine of 150 is. Cosine of 150 is equal to negative root 3 over 2. So what that tells me is that this big long expression is also equal to negative root 3 over 2. Now for part B closely resembles equation 4. So the angle that we're dealing with here is 45 degrees. So when I double it, I get that the sine of 2 times 45, or 90 degrees, is equal to 2 times the sine of 45 cosine of 45. So now we take a step back, we look at the problem, and we ask ourselves, is this right side a match for this problem I'm trying to solve? And it is. It's a direct match. So since it's a direct match, then I'm ready to go ahead and solve the other side. I can say, all right, well, what is sine of 90? I know that the sine of 90 is equal to 1. Therefore, this expression is also equal to 1. All right, now not all problems are going to be a direct match when we first look at them. And example C is going to show us how that's going to look. So when I look at example C, first of all, it doesn't exactly match any of those formulas. We know that it doesn't match the first one because there's no sine squared. For the same reason, it doesn't match the third formula, and it definitely doesn't match the fourth formula because we're not looking at a product of sine and cosine. So for that reason, we know that this one closely resembles formula 2. We see the cosine squared, we see it subtracting a value, and so that tells me that, hey, yeah, it does match equation 2. Alright, so now that we know which one it closely matches, now we're going to rewrite it the way that it should look. So I know that cosine of 2 times the angle, and in this problem the angle is pi eighths, so cosine of 2 times pi eighths should equal 2 cosine squared of pi eighths minus 1. So now what I'm going to do is I'm going to come over here and I'm going to ask myself, is this equation a match to this expression? and it's not a match, but it's close. It's close because if I were to divide both of those terms by 2, then it would be a match. So what I'm going to do is I'm going to divide all terms by 2 so it is a match. So I'm going to divide this by 2, I'm going to divide the 1 by 2, and I'm going to divide my cosine expression by 2. And what I end up getting is 1/2 cosine. If I simplify that, I just get cosine of pi fourths equals cosine squared pi eighths minus 1/2. So now we ask ourselves, do I have a match now? And the answer is yes, I do. I have a match. All right, so now I go ahead and I solve this. 1/2 times cosine of pi fourths is root 2 over 2. Therefore, my solution is root 2 over 4. All right, pause the video and try the last examples on the next page by yourself. All right, if we look at example D, this one closely matches our first equation. So I wrote it the way that it should look. Cosine of 60 equals cosine squared 30 minus sine squared 30. And the issue here is that on the right-hand side, the signs are wrong. I need to multiply this equation by -1 in order to get the correct signs. Therefore, I also need to multiply the left side by -1. So that means that negative cosine of 60 degrees equals negative cosine squared 30 plus sine squared 30. Now that my right side is a match, I can go ahead and solve my left side, getting negative of 1/2 as my answer. When I look at part E is a little bit more tricky. People look at this one and they say, okay, well it kind of looks like my third formula, but there's no 1 there. All right, well, let's start by saying what it should look like. It should look like cosine of 2 times the angle, so cosine of 45 degrees equals 1 minus 2 sine squared of 22.5. So if we compare this, it looks almost the same. The only difference is that my target doesn't have a 1 there. Well, how do I fix that problem? I subtract a 1 from both sides. So if I subtract a 1 and subtract a 1, now I have a match. So if I go ahead and simplify cosine 45 and subtract 1 from that, that will equal -2 sine squared 22.5 degrees, which is what I am trying to solve for. So my answer will be root 2 over 2 minus 1. In problem F, we should recognize that this matches my sine double angle. So sine of 30 equals 2 sine 15 cosine 15. However, I don't want that 2 there, therefore I have to divide both sides by 2. So now on my right hand side, after dividing by 2, I now have a match. Therefore, I'm ready to go with my left hand side. Sine of 30 is 1/2. 1/2 times 1/2 gives me 1/4. And then last but not least, this one some of us did in class the other day. We take a look at our formula. It looks like the sine double angle formula, which I have written in red. However, it's not a match the way that we see it. We have to divide it by 16. Once we divide by 16, we have a match on the right. Therefore, we can go ahead and solve on the left. And that's what we see here in green with 1/16 times root 2 over 2.